So, hello everyone. My name is Benny. I work on Contigo with, doing StarCross and stuff like that. And I also, during my full-time job, work at Niantic Labs working as an AI platform engineer. And today, I'm here to talk about this kind of term I coined for this way of programming that I like to use, which is called everything-oriented programming. And what exactly that means. So before I actually explain what everything-oriented programming is, I like to actually explain kind of the history of how it actually became a thing that, I made a term for and can actually give a definition for and things like that. So, starting a very long time ago, in the distant year of 2009, I was just starting to get into game design in I think it was middle school. When I was starting with game design, I started with a tool called Game Maker, which taught me okay, here are your game objects, you can make scripts for them, and make them do things and things like that. So I started with that, and then I eventually kept switching tools as I just found different things that I liked. I moved to Torque and then eventually Unity and Unreal once I was in college, and I picked up some other programming languages along the way to do things that weren't games. And so the thing was, with kind of this pathway of how I learned how to program and also how I learned how to make games, it kind of set me on a pathway for what would eventually lead to me figuring out what everything-oriented programming was. But all of these things have something in common, which is that they're all object-oriented tools. They all rely and teach object-oriented principles for actually making your games and making your game code. And so as I started nearing the end of college and my games started getting bigger and using more code and classes and things like that, I started to notice that there was kind of a problem with all of my code, and I would always run into it. Basically every time I would start a game project, things started out pretty well. I could create classes really well, I could use inheritance to share code between things, make my code really nice, things like that. But every time it started growing bigger, I always encountered the same problem, which is that I had all these pieces that kind of wanted to share things between each other. So players and enemies, they may be similar, they may share a lot of pieces, but they may not share everything with one another. And no matter what I did with the object-oriented stuff that I had learned, I could never quite figure out a way to make this work. I always reached that point where things just stopped scaling well. And so the problem was I didn't really, at this time, understand what was actually the root cause of this problem. I couldn't find any vocabulary to be able to actually describe this. And so I started to do lots and lots of research into design, and I got very interested in how do you design code. And so eventually, where I'm at now, I kind of figured out that one of those root problems was kind of like Plato's allegory, with the cave and the shadows. In this, basically you have people who all they see for their life is 2D shadows, and that's all they know the world to be. And the same was true with object-orientedness. All I knew was how to program in this one way, and because of that, that's the only way I knew how to really talk about programming. And so kind of to figure out what this problem actually was, I had to start learning more ways of programming and introducing more ways of that, and being able to actually expand my vocabulary so that way it would include ways to actually describe what this problem was. Okay, so that took me a long time to actually figure out how to do that, and I only have an hour, so we're just going to jump right into understanding what that actual problem is. So, how many of you are familiar with object-oriented programming and use it regularly? Okay, cool. So for the invisible group of you online who maybe didn't raise your hands, Object-oriented programming, in a nutshell, is kind of based around the concept of you organize your code into types. It's kind of a very human way of organizing things. So, like in science, we like organizing animals into, classes and kingdoms and things like that. Everything kind of inherits from each other. Object-oriented programming is kind of the same principle, but with code. You can write code as kind of a type of object, and then you can write other pieces of code that inherit from that type of object. And they will share everything, that their parent has and be able to expand upon it. And so like a really good example here of kind of what that structure looks like is you have a vehicle. That vehicle can be, a boat or a wheeled vehicle. Both of them inherit from vehicle, so they share everything about vehicle. And same with wheeled vehicles and all the way down the tree. And so, from a code point of view, this is nice because it allows us to define kind of like, okay, here's a base piece of functionality. I can say that, my root type, like the object, has the ability to do these things. And then, the type person has the ability to do these things and so on and so forth. So I can keep expanding things out, and it's a nice structure because, it's easy for us to understand. Like, oh, yeah, types, inherit from each other. They're related. Okay, so to understand where the problem comes in now, I find it's good to start with an example problem. So for this, we're just going to make kind of a very, very tiny game. It's going to work kind of like a real game. We're going to have a list of constraints that we need to implement, and that list is going to slowly grow over time. So we're going to start with basically this game. It's a great game of the year. We're going to have players and enemies. The players and enemies can both move. They both have health, but the player moves based on input, and we're not going to specify how the enemies move, but we do know the enemies move. If you all want to take like 20 seconds to kind of think of a code structure in your head of what this would look like, or just stare at the slide if you don't want to do that, go ahead. Okay, so the basic object-oriented approach that I use to solve this problem looks something like this. So, if any of you have used Unreal before, you have probably seen these exact class names. So I created a base type called pawn, which is just generally speaking a thing that exists in the world kind of as a controllable entity. So the player is a pawn and the enemy is a pawn. They can both move around, they both have health, and they both have this update function. And so this allows us to get all of the constraints that we want. We can, the health and the moving, that functionality was shared in our constraints between both player and enemy. And so with this structure, we're able to share that nicely because pawn can contain that functionality, and it will share it between both its inherited types. However, with player, we specified that movement needs to happen with input. And so one of the things that we can take advantage of is this on update. We can override it in the player and specify that on update, we're going to read the input and call the move in a certain direction based on that. And in theory, we could do a similar thing with the enemy, but based on some other criteria, if that ever became a thing that we wanted to add. So, if we expand the constraints a little bit more, we're going to add now boxes, and boxes can take damage, but they don't move. So we still have players still move, things like that, but we're now adding boxes, they don't move, but they do have health. So again, kind of the basic layout that I created for this looks something like this. So without expanding, creating any new types beyond the box, or without modifying any of the types that existed and only creating a new type for the box, this is an approach that I created. Basically, we just create a box and it inherits from pawn as well. This gives us the shared functionality for health between all of our three types, but there's a little bit of an inconsistency now with our code and what our constraints were. Our constraints specified that the box can't move, and we have a move function that's on the box. Now we could just never call move, and ta-da, you're done, your box doesn't move. You met technically the game constraints. But from a code point of view, this is a little weird because we specified that a box shouldn't move, and if I'm some new person on this project and I'm looking through your project and I know that a box can't move and I see the move function on a box, I will get very confused as to why a box can move. So this isn't maybe the best way to approach this. So we can approach this a different way by actually modifying our types to ensure that we share the functionality we want to between the box and the pawns, but we don't share all of it. And we just do this by introducing a new, more base type. This new base type takes the health and the hurt and shares that with the box, but it doesn't have movement on it. And so because of that, our box has all of the constraints that it needed, but it doesn't have anything more than that. And the player pawn and the enemy, they both share all of their functionality still, and they share it with the box, but so they get everything that we want, and we meet all of our constraints in a way that makes sense. Okay, our last set of constraints. We want to set things on fire. So, the boxes we want to set on fire. The players we want to set on fire. But enemies we don't want to set on fire. Who knows why we don't want to set enemies on fire, but that is a constraint that we are being given. They cannot be set on fire. So, the question becomes, how can we make a structure that holds these constraints as well? Again, there's kind of multiple approaches that we can take to this. So we know that only the player and the box are going to be able to be set on fire. And so if we wanted to kind of follow this model of we don't want functionality on things that don't have the functionality, then we can accomplish it this way. We can put ignite on the player and ignite on the box. And by doing this, they both have their ability to catch on fire, and the enemy does not. But this adds a downside now, where if box and player have the same exact code for ignite, they're not really sharing it. So if I wanted to be able to share it, I could put it in actor. But by doing this, I have also now introduced it in the enemy. And so now, unfortunately, I can't add a type in like I did with the actor and the health. There's too many, in order to keep the inheritance pattern of a tree, I wouldn't be able to do that. And so now I have to make a decision. Do I either want to keep the actual constraints real and give up on being able to share this code? Or do I want to be able to share this code and give up on keeping the constraints real? And so this is what I refer to as the tree problem. So when you're using object-oriented inheritance, your model looks like this. You can think of your branching as pathways, and effectively, if you want to know how easy it is to share something using only inheritance between 2 points, then you can figure it out by drawing a path between those 2 points and effectively seeing how high it goes. If I want to share it between 2 nodes that are incredibly close, it's really easy. I just draw a short path, and I can see that the place where because it's actually visible, but the place where I get to share it is that node that's right above them. But if I wanted to share something, say, between 2 nodes on opposite sides of the tree, then I have to go all the way up to the top and then all the way down to the bottom, which means that I am potentially putting things that are shared between all of these other blue nodes that probably do not need whatever functionality I'm sharing. So, there is an easy way around this. We just stop structuring things as trees. What if we were just able to draw a line between those 2 nodes? all of a sudden we don't have this problem anymore. We've directly connected the pieces that we want, and we've shared it. So the question becomes, is there a way to actually do this through code? And I wouldn't have a talk if there wasn't, so. Yeah, and so this is kind of what the root cause is. The root cause is that we are kind of forced into this tree structure by object-oriented programming. And the reality is that the tree structure is just, if I go back, when we start thinking about this tree structure as not a tree structure, but really a graph, then really these lines represent relationships between different pieces. And the problem becomes easy to solve then when I just am able to make a relationship between two of the pieces. So all design problems kind of have this, all design principles kind of have this problem at some point if you follow them to like the letter. If you're doing object-oriented programming, obviously it has that, I just showed it. But even if you're doing functional or ECS or pipeline or whatever, if you follow it to the letter, you will at some point hit this problem. And the problem is due to the fact that, just the fact of the way these relationships are structured. And so this is kind of the key to everything oriented design, or everything oriented programming, is programming with these relationships. And so that's the next thing I'm going to talk about. Okay, so real quick, when I say a relationship, what do I actually mean? So what I'm describing is a logical relationship. So for anybody who's done database programming, you might know, kind of what the concept of a relationship there is. And this is a very similar concept. It's basically, you have two pieces that are inherently interacting with one another in some way. So, this might be, through function calling, or it might be through inheritance, or whatever. Any interaction at all is a relationship. And so relationships can come in all sorts of forms. So, as I said, function calling, inheritance, things like that is a relationship. Pretty much any type of interaction you can put in your code is going to be a relationship. Even with this very simple structure, we have a relationship. I've defined, a vector 3. A three-dimensional vector is just a x, y, z of floats or doubles or whatever you want to do your position in. There is a relationship there. You've defined a relationship between this new type that you've created and the type float. And this relationship is a relationship that defines a lot of things, has a lot of rules to it. It defines out what is actually being represented and how these things are able to interact and so on and so forth. So if we dig a little deeper, what are we actually making related here? So if we take any piece of code, like this piece of code, we can always break it down into two basic components. We have logic and we have data. So data is, effectively just structures. It's just memory about things. Data can store all types of things. It can have rules about how things are stored. So if you think about, say, a linked list, that is a data structure, and there are rules about how that data structure has to be formatted and things like that. But data cannot change by itself. If I define a piece of data and do nothing with it, it's not going to change ever. Data has to be acted upon by its second piece, which is logic. Logic is the piece of your code that actually does things. It takes in data, it does calculations, and it might spit out more data, so on and so forth. Logic itself can't have storage. It is just an operation. So here with my example of health, I have my health defined as a structure of a value, and then the actual interaction with damaging it, or maybe healing or whatever, that's the logic. Yeah, and so pretty much any program that you can write can always be broken down into this, its simplest form of logic and data. Here I have a program that's just a very simple player, and I can break it down into just simple logic and simple data. And then I can graph out what the relationship between all of these things are. I can see there's relationships between data and data, and I can also see that there's relationships between logic and logic, and at the very end, there's relationships between logic and data. And one of the key things here is that each of these relationships is not quite the same. The relationships represent different things. With the logic, we're representing a call chain. With the update player, the kill player, I don't know how well that code is readable from the back, but basically we kill the player when the health is 0. That relationship is a special relationship because it's conditional. It's not always going to happen. But the one to damage is also conditional, and those relationships are also based on the relationships update player has with data. It's hard to represent all of this in a graph, but if we were to really go through the code and kind of write out what all these relationships were, we could see all of this. One thing that's important is, you might be thinking, well, when I write my code, I write code that's not just I have a function and it takes in things, it's a part of the thing that I created. And that's true, but you can still always break this down. So, if I were to write my health data in a more probably common way, it would probably look like this. And the thing is, this is what I like to refer to as an implicit relationship. Technically, this is the truest form of what your logic and data is. They are still separate. However, the language is adding an implicit way of doing this. It's giving you syntax that makes it really easy to be able to just say, okay, I have this thing, it's always related to this data structure, and that's never going to change. And so all throughout programming, there's languages that add a lot of different types of implicit relationships. When you're using any sort of object-oriented programming language, it has a bunch of implicit relationships with defining how things are inherited. If you went into C and tried to define how things are inherited, you would find that it's actually a lot of things under the hood that C is doing for you to create this very complex relationship model. And so that can be helpful. It allows for us to not necessarily have to worry about all the inner workings and rules of these relationships. But it is important to understand that they are still there, so that way you can, at least mentally break things down. Okay, so we now understand what a relationship is. We understand that they, we can use them to see how code ties together. But why is this actually helpful to us? Okay, so designing with relationships. So if we go back kind of to looking at code patterns and code models, if we start thinking in terms of relationships, code patterns become really simple to understand. It allows us to, rather than thinking of them as, okay, here's a pattern of steps that I need to take, or a pattern of placing classes and things like that, it really just becomes a pattern of a graph. Here is my relationship pattern. Here's how the things relate, and so on and so forth. Here's the type of relationships that I use. And so, we can see this with, if we go back to object-oriented programming, then we can see this in what our problem was. Our problem was that we were kind of using the abstraction of what object-oriented programming was. But if we actually break it down to its relationship model, then we can understand how we are actually interacting with things. We can understand what the pattern of that type of programming is. And this becomes really powerful because it allows you to kind of weave patterns together once you understand what their actual graph model is. Here, if I'm using, object-oriented design and, pipeline or functional or whatever you want to call it, it doesn't just become a one or the other. I don't have to choose necessarily. I could weave them together to get the best design that I possibly want. If I break these two design patterns down to what their actual relationship model is, it can become very clear of, oh, I can use this and this together in this way that is helpful for the task that I am trying to accomplish. And so this becomes really helpful as you start building up your projects. I can take, as I'm growing my project, I'm going to be using, relationships between all my different things in order to actually, make my game do what I wanted to do and things like that. And the thing is, if I come across a problem, I don't have to just solve it using object-oriented programming because that's what I was using, or functional programming because that's what I was using. I can kind of look at patterns that might already exist in the code or maybe exist somewhere else, and I can grow out my project naturally by using those patterns where they make sense. And so kind of an example of how this can really be used is, how many of you are familiar with ECS? Okay, so I will actually describe ECS. So ECS is the new hot thing. It stands for Entity Component System. It's kind of this, put it in very simple terms, the way that you program using ECS is rather than you putting your logic on your actual objects, you make your objects just data. So usually, you can kind of think of it as like, kind of columns of data or as, entities or whatever. But basically, you have these entities that are just composed of components. These components are raw data. And then you have these systems that basically update periodically in order to do some form of a task. They query for all of the components in the world that they care about, or all entities in the world that contain components that they care about, and then they operate on them. If we break this down into a relational model, it looks something like this. The purple is our data. We just have a clustering of a bunch of data that is all related to each other in different ways, but for the purpose of this, we're just going to think of it as one cluster that we're going to kind of poke into with our green, which is our systems. The systems are going to use this data to do things, and because of that, we kind of get this relationship model. So the thing is, using other patterns with ECS can be very helpful. It's pretty common that you'll have logic that you want to be able to make common. So, you can imagine a scenario where you have a system that, let's say let's say you create a base class for a certain type of system that allows you to do a certain form of operation very helpful. So maybe you have like let's imagine you have both 2D and 3D physics in your world. It'd be helpful to create just a general physics system that accomplishes a lot of the logic that is shared between them. And then you can have your 2D and 3D physics systems inherit from that. Using the inheritance relationship here, along with my ECS relationships, helps me to build stronger code. It allows me to choose points at which the object-oriented inheritance is helpful, while also taking advantage of where ECS is helpful. Okay. There are other parts where this form of kind of breaking things down into the relationships becomes helpful as well, and that is with performance. So if we stop talking about relationships for 5 seconds and ask ourselves another question, which is, what causes unperformant code? There are a lot of opinions on this, so I tried to generalize. But basically, if we do some math, generally speaking, computers are fast nowadays. Even your phone is still like many times more powerful than an Xbox 360 was when it came out. And so if you do some math, like pretty much everything that you can do on a computer, that computer is going to be able to do, billions of calculations every second. And so because of that, your performance generally doesn't come in little small things that you're doing, performance problems come in when there is something that adds up over time. To basically be the same magnitude of, how much the CPU is calculating. To kind of give a small example of that, like sorting a list. Say you have a list of 50 things and you want to sort that list every single frame. That's nothing. Like, that is not a performance issue at all. Even though it seems inefficient, and there probably are more efficient ways to do it, it really isn't worth it because the CPU is so fast that doing a sort on 50 items is non-noticeable if you did it any more efficiently. But if you boosted that number up to 5 billion, items, you would probably start seeing performance issues pretty bad. Yeah. And so the things that generally add up have to do with, just not using the computer in the way that it, is optimal for. So doing things like allocations or incurring cache misses, or not utilizing all of the cores on your computer, or doing things that trigger large calculations like garbage collection. These things, when done in large numbers, will make your code unperformant. And the thing with all of these things is that, generally speaking, what causes this, the root cause of this, is not, I chose to do something wrong in this one area. It's, I chose to do something wrong structurally with my program. And so this is one of the things that's really hard with making a performant program, is that, generally speaking, people are, trying to focus on like, okay, how can I make this algorithm faster or this piece faster? But, understanding the actual structures of how can I structure everything together so that way I'm getting the most performance out of my, game or program or whatever, that's really hard to actually do. And so, like here with, object-oriented programming, we can kind of see that when we break it down into its relational model, there's not a whole lot here that helps with performance. This is one of the great things with thinking about things in relationships, is that it becomes clear how your data and logic is actually being related to one another. So if you want to make it performant, just start structuring that relationship in a way that makes it performant. I'm going to use ECS again because that's one of its big things is performance. This relationship model is set up in a way that is helpful for a lot of the things that we're trying to get rid of with unperformant code. We've taken our data, which here was scattered all over the place, and our logic, which is scattered all over the place, and we've arranged it in ways that for one puts the data close together. So that's going to get rid of cache misses. We've set up the data so that way, rather than it just kind of randomly being accessed from logic, is organizedly being accessed from logic. And so because of that, we can better understand the timing of when different pieces are going to access it. And even better yet, we could, in theory, parallelize those if we know there's two pieces that are unrelated to one another. We can understand the chain of events that systems have to do and how those systems are actually related to each other. And that also gives us a bit of benefit in, making faster code. It, allows us to see how pieces of logic are actually interacting and maybe, organize things in a way where, if we execute this and this together or next to each other, we see a benefit because we know that these two calculations being done one after the other rather than maybe randomly over time is going to give us a performance increase. Okay, cool. Yeah, and so, I basically went over this, but relationships help with this. They help with us being able to break down our program into kind of, as I mentioned at the beginning, a vocabulary in which we can understand how everything is kind of going together. And we can easily see how this relationship would impact performance. And even better yet, we can move things around in a way where we know, this is going to create a better performance model. And best of all, it allows us to do this all without necessarily sacrificing our design. One of the big things I know, that a lot, that's a lot of balance between performing code and well-designed code is sometimes when you choose a certain design, you sacrifice some performance because it makes your life easier. And so the thing is, if we understand how things are relating, we can find a nice balance that's not necessarily a complete sacrifice, and even find a relational model that gives us all the performance we want while still giving us the relationship capabilities that we want to have. And so kind of to sum up my beginning question, which is, what is everything-oriented programming? And so I created this definition for it, which is, it's a model of programming that is based on the relationship of logic and data. All interactions between pieces of code can be described as relationships. By doing this, the programmer may model the program using any and all architectural models depending on what best suits their needs, making it oriented on everything. In other words, you can break down your code into a very simple understanding and kind of structure it however is best for you. And by doing that, you gain a better understanding. So kind of ways that you can get started doing this form of programming, rather than just necessarily jumping in all at once. If you jump in all at once, that might be hard to do, especially if you've only learned one form of programming so far. And so generally what I would give as a good way to get started is start trying to program with other types of programming models. If you're doing a lot of object-oriented, maybe try making something that's purely functional, or try making something that is purely data-oriented or something like that. Kind of get outside of your comfort zone. And while you're doing this, keep in mind what the relationships between all of your pieces are. Think about, with using this model, this is how things are related to one another. As you learn more and more models, you'll eventually learn kind of what their pros and cons are. In this model, this relationship causes these problems, but it's really good at solving these problems. And so you'll get better at understanding where certain models can be used. And even better yet, you'll get good at learning where certain types of relationships can be used in order to give you advantages. I would also recommend, if you're maybe not going to do an entire project or something in a form of programming, or you don't necessarily know like a good way to do it, try just watching talks on a bunch of different models. I kind of gave a list here of ones you can start looking at. These are basically a list of buzzwords that are popular right now. There's a lot more beyond this, but I think these are good ones to kind of start with. And there's a lot of talks on them, so you can get a lot of opinions on it and stuff like that. And kind of while looking at these talks again, think about, okay, what are the actual relationships between all the code here? Like, why is that benefiting this? What are the downsides of those relationships and things like that? And then finally, like, the way that I came up with kind of this model or philosophy of programming is just experiment. Like, try new things. You might have a crazy idea for a certain type of, if I relate things this way, maybe it could allow me to do this thing. And the thing is, you will only know if you try it. I've definitely done that a lot with my code, and I've definitely had a lot of pieces of code fail because of that. But I've also had a lot of pieces of code, go, do way more than, what they necessarily needed to do, and be, very good pieces of code or good APIs or whatever, because I experimented. And just by doing those experiments, I learned exactly what things work and what things don't work. And that is everything-oriented programming. Questions? Just gonna stand here for the next 20 minutes. It's a take your time.